Yesterday you were introduced to two new concepts, period and frequency. When you are looking at period, you are considering how much time it takes for the object to go a full cycle. A full cycle means starting at its resting position and returning to its resting position. We looked at a pendulum yesterday. That would mean going up to the right side, coming back down and going to the left-hand side, and then back to the resting position at the center. What would that be for a wave? So let's say this is the resting position of the ocean. And we have a series of waves coming towards the beach. What would you consider to be the one full wave?
From crest to crest.
Okay. From here to here?
Or to the next one maybe? Because then it's a full. Yeah.
Yes. You need a full crest and a full trough. That means that from here to here is actually one full wave. So if you have 5 cycles,
Drops.
five crests, 5 troughs. If you have 5 cycles, 1, 2, 3, 4, 5. 5 valleys, 5 hills. We use a proper time terminal. 5 crests and 5 troughs. We're going to time how long it takes to make those cycles. Why would we time a number of cycles rather than just one? Why would we time a number of waves rather than just try to time one wave?
Because it could be a different frequency.
Have you ever tried to keep track of the waves coming onto the beach? I think we need to go to the beach more often.
Yes, I try to make sure that I read.
It can be really challenging. The waves are coming in quite fast. Sometimes it's easier to count 10 waves coming into the beach and time those 10 waves rather than to time every single wave that comes into the beach. That means you're getting an average. It might not be a true representation of the time it takes for every single wave to come in. There can be some variance. Frequency is the number of cycles that are completed in a particular time period. So what you would be doing then is standing on the beach looking out at the water body, and you would be turning on this and counting how many waves come to the beach in those 5 minutes. So period and frequency are related. They're called reciprocals of each other. They don't measure the same thing because they are reciprocals. Yesterday we left off with a question saying that electrons vibrate with a frequency of 60 hertz. You were asked to calculate the period of that vibration. Oh, sorry, no, it was 30. We were asked to.
Yeah, 4.
It was question 4. Thank you. Usually I leave a post-it note or something. Okay. If you have 60 hertz, is hertz a period or is hertz a frequency? It's a frequency. Okay. 1 hertz is going to be equal to 1 cycle per 1 second. If you were told that you have a frequency of 60 hertz, that means you have 16 cycles per 1 second. Now, it's asking you to calculate frequency. Frequency is time divided by cycles. So that means 1 second is divided by 60 cycles. You need to reduce this to over 1 so that we can see how many seconds it will take for 1 cycle to happen. One divided by 60?
0.
Okay. How many seconds do you get? Just one. So it is 2 times 10 to the negative 2 cycles per second. Or seconds per cycle. 60 only has 1 second. So you only get 1 significant. There's another way that you can do this quite easily. Take a look at your calculator face. Do you have a 1 over x button on your calculator face? Some of you might have it. Some of you might not. You can find out a reciprocal number quite easily by using the 1 over x button. For example, if you type in the number 60 and then hit that button, it will give you that answer. Because period is a reciprocal. I don't have it on this console, but on my console at home I have a whoa. What I'll do is I'll try to ask this calendar today if there's another button that has replaced that. So that's
I'm nervous for that presentation. I know.
and then we'll all set about that. I'll talk to Miss Hamilton and see if there's another button that will do the same thing. Try it, Matthew. See if that x to the negative 1 will work. You did? Okay. So try this. X to the negative 1. Do you have that? You function 60 and then you have that. So you could get 2 times 10 to the negative 2.
I tried that, but no. You get like 60.
Go equals.
Oh yeah.
Alright, so thank you, Matthew. That should work. Well, we'll practice that a few times just to make sure that we get consistent results in case they're not bad.
But
Yeah, this is a
Alright.
what?
What I want you to do is you have question numbers
This one I understand.
5, 6 that I would want you to try. Question 7 we'll work through together because it has the prefix omega. And I'm not sure how many of you are familiar with that set of units. Okay, so question number 5 is looking at the tuning forks. The tuning forks are what we used yesterday. In order to look at vibrations and be introduced to the vibrations. So it says that your frequency, which is this one here, is 1.0 times 10 to the negative 3 asking you to calculate the frequency. It says that it has a period of 1.0 times 10 to the negative 3 seconds per 1 cycle. This is your time. This is your M. You're taking out and you're doing the same amount. Which means that to find out your frequency, it is 1 cycle over 1.0 times 10 to the negative 3 seconds. You need to reduce that so that it is a number over 1. One divided by 1.0 times 10 to the negative 3 is 1.0 times 10 to the positive 3 cycles per second. The reason why this has 2 sig figs is because this is for exactly 1 cycle, which means 1.00000. It is exactly 1 cycle. So you can remember the zeros after, and you can look at that number for sig figs. Look at the original in order to determine the number of sig figs in that calculation. So, calculate frequency. It is the flipped version of the period, which means that there's a second formula for doing frequency. And that formula is 1 over your period. Okay, you just take it over your period. So you could do this as 1.0 times 10 to the negative 3, and then period x to the negative 1 button, or the 1 over x. Similarly, period can be calculated by taking 1 over frequency, because it is also very cyclical of it. So that can make things a little bit shorter. Question number 6 is a little bit more challenging. Question 6 tells you that you have a duck sitting on the waves, and the frequency of the waves is 0.25 hertz, which is cycles per 1 second. is sitting on the wave for 5 waves, 5 cycles. How long does it take to death? So these 5 waves. One wave is 0.25 seconds. Second wave, another 0.25 seconds. See where this is going? Kind of, sort of, not yet. And the third wave is 0.25 seconds. The fourth wave is 0.25 seconds. The fifth wave is 0.25 seconds. How much time is that? Okay, so it's going to be 1.25 seconds. So each wave of axis is 0.25. That's more of a logic problem. So it's not just talking by formulas. Visualize what's going on and see what period and be able to actually apply that. The whole broadcast at 104.9 megahertz. Is that frequency or a period? Hertz is a frequency. If you're not sure, I would suggest that you write it on the frequency. If it says that you have 104.9 megahertz, we need to convert that to get hertz. So we have what we need over what we have. Do you know how many base units are going to make it? So for example, bytes. If you use a flash drive, or maybe you made this decision when you're buying your cell phone, gigabytes, megabytes. So if we have the byte, how many bytes would be in a kilobyte? 1,000. Next comes mega. How many bytes would be in a mega?
10,000.
Million. Go up by 1,000 every time you go up the step in the measure. There would be 1 billion bytes in a gigabyte. So this is 1 times 10 to the 6 hertz in 1 megahertz. And that is going to convert you to hertz, which is 1.049 times 10 to the 8. A hertz is a cycle per second. Asking for period. You can either do the time divided by the n, or take this number in your calculator and press the X-1 button, has period is 1 over frequency. Is going to be 1 second over 1.049 seconds.
A lot of zeros.
Very, very small. Try using that x negative 1 button. Okay, we should get 9.533 times 10 to the negative 9 seconds in 1 second.
That's just because.
That's fine. Oh, I know that is true. Oh, it's positive.
It's positive.
Oh, it is positive? It's absolutely from here. I'll just go shift and then the X minus 1.
Yeah.
See it there? That's okay. And then this is still what I get.
This line 1 divided by 1.049, and then it's multiplying it by 10 to use test that I have 1.049.
No, we don't have to. Yeah, we should. We can delete that part, but I like the ball.
Oh, great. Are you have the same calculator as I do?
Yeah. I found 0.009.
Yeah.
If I go to multiply that by 11,000, you'll see those 10 numbers there. I'll bet you I can multiply by it. I'm gonna forget to do that because you'll see like that 0.532 something.
So we have to multiply.
To be able to see those numbers.
Why can't we just do like that?
I'll ask.
Oh, we do.
Oh.
Because so you need to try and find these numbers behind that. So we have to multiply by 1,000. So then to multiply by 1,000, that's what you were doing first, and I don't know what I did. What one? I don't know, but I don't know how I did it. I just walked around and go, and I looked at my phone, and it was kind of
That's not very
I don't know what I did. I almost because I wasn't wearing shoes, and then when I was outside, and the ball went on the gravel road, and I just kind of walked down the gravel road. That's not good stuff. Why is it called Band-Aid? It's also called Band-Aid. Band-Aid. It's aid. That's bad. That's sad. What happened there?
It's just hard to manage.
What is this?
This hopefully can learn this is a transverse study. Instead of looking at a pendulum going back and forth, we're now looking at something that has three-dimensional motion, not just SMI motion. Imagine that you have your swinging pendulum. Okay, so what I'm going to do is just try this highlighter. Yesterday, keeps going back and forth like this. What if take this? So where's the rest position? So instead of looking at this as side-to-side motion, and look at that. So the amplitude, go back to our original example, here's your position at rest. For a pendulum, the farthest out it swings is the amplitude. And it goes back to rest, it swings out this side, and have a second amplitude. So if I take this and I rotate it around, this is our rest position here. Our amplitude is from the rest position to the highest point of the past, and to the lowest point of the trough. A wavelength is from the crest of one wave to the crest of another wave. Or you can do from one trough to one trough, or as long as you take the same starting point and same finishing point, for example here and here, this is also representative of one cycle. So you start here, you go up to this amplitude, you go down to the other side, and you return to your rest position. One cycle. What we're going to do is apply some of the things that we learned about frequency and period to waves. So instead of just thinking two-dimensionally, now we're going to think three-dimensionally. In question number 6, you have a couple of different wavelengths. Here. Where is the best position for these waves?
where the hole in the paper is.
Doesn't really help me be a smartphone. The easiest way to do rest position is look at here, where it starts, and here where it ends, and then use a ruler and connect the two so that you have something like that. And do the next same thing for the next diagram here and here. And you can do your rest position here and here. Draw in your rest position. Here I can't quite see where I left off, but it's somewhere down here. So that would be your rest position there. Line would I suggest doing your amplitude, or say doing your rest line.
Figure out something a lot easier.
Take a look at the next question. It's going to ask you for which one's the biggest amplitude. What is amplitude?
I'll pass through.
From the rest line to the top of the crest, or from the rest line to the bottom of the trunk. So not how rest line is that? It's really hard to measure the difference. So I suggest you draw it in so that you can take your ruler and start measuring some amplitudes for comparison. Which one of those three waves
Hey,
has the biggest amplitude?
hey.
Wanna get it?
Well, you gotta add it.
Okay. Wavelength. What do you measure?
How long is it? Like between the two waves?
Okay. So, when you're doing that, be consistent. That's my greatest piece of advice for you here. Okay. So if you choose to measure from the top of the crest to the top of the crest, stay with that. If you choose to measure from the bottom of the trunk to the bottom of the trunk, keep that. What do you do if you have only one crest and one trunk?
Measure from the middle of each rest point.
Okay, so when you say middle, what do you mean?
Middle of each wave.
Okay, so middle of the wave there to here.
But keep your ruler.
Ah, yes. Okay. So from here to there, will give you one wave. Because that's the start and the finishing place. How about for the last option, where you only have a crest? Yes, that's exactly what you do. Did you hear what Mason suggested? This crest represents half a wavelength. So you would measure from here to where it comes down here, and you would double it in order to get the total wavelength. So please measure wavelengths and then determine which has the shortest wavelength and which has the longest wavelength. Which one has the shortest wavelength and which one has the longest wavelength?
Oh, I have to.
ACD. ACD. ACDC.
PC? Okay. That's pretty good songs, actually.
And they have wavelength sound.
That's true. So shortest wavelength is C.
Yeah.
Longest wavelength is D. Okay. So, let's say that each of these pictures, A, B, C, and D, are snapshots. And they are a snapshot of the wave over a 1 second